Hello, everyone. If you can't hear, I can't hear as well. So in case you were curious, we might be having some audio issues. Let me know if you can hear me at all in the comments, because that would be nice. Okay. I will ad-lib for a while. I also don't have a camera because I've taken it off to use it for something else. So um, you won't see me, you'll just hear me, which is super fun. Um, I hope everyone's semester is going well. um, it's just my voice. Um, it'll just be me. I finished my master's. That's super fun. what what masters did you finish? This will just be fun club bonding time. And I will sit here in silence and talk to myself. Just classic IT. Hello.
Okay, I think I fixed it. Hello?
I can hear you. So I'm going
Okay, amazing. That's
to
really
hear
good.
you. All right, goodbye.
Okay, hi everyone. Today I'm going to be doing a workshop on binary exploitation, specifically some heap overflow stuff. But before we get started, there's a quick announcement. Let me just look it up. I just wanted to remind everyone that we are going to be having the next installment of our speaker series, and we're going to be joined by Dr. Jason Jaskolka, who will be presenting to us the security of multi-agent systems. And if you want to attend the speaker series, you gotta. It is for premium members only, and you can become a premium member by e-transferring $5 to the infosec.ucalgary@gmail.com, and we hope to see you there. So, with that out of the way, I think we can probably get started with the. Oh, where did my slides go? Oh no. Okay. Oh, there they are. Okay, cool. So we can get started with the workshop. All right. So, okay, I think I have everything. So today we're going to be doing, like I said, binary exploitation, heap overflows. Our goals today are going to be understanding what a heap overflow is, which is not very different from a stack overflow. And we're going to be also trying to achieve some arbitrary code execution. Just right. Some relevant courses. Courses that are probably relevant to this are Computing Machinery 1, 2, and Principles of Computer Security. So if you've taken these, then you're probably not going to have too much trouble with this. But if you haven't, I've tried to make this as accessible as possible. Tools we're going to be using today are GDB and Pwn tools. We're not going to be using too many things. And also that reminds me, I need to post the files everyone needs to download for the workshop. So if you can look in workshop materials, so I'm going to ping it with an ad here. I'm going to actually, I won't ping it with an ad here because that'll ping everyone. So just I'm going to post it in the workshop materials. Okay, so that's posted there. Some prerequisites for this course are going to be by prerequisites, I mean things that you should at least be familiar with, because I'm not going to be covering them in great detail, but you don't have to be like an expert or anything. So strings, characters, bytes, bits, ASCII, buffers, buffer overflows, and ASLR. Okay, so some quick review in the context of C. Can anyone remember, if hopefully people will remember, the difference between a heap and a stack. The main difference being that a heap is kind of just all over the place. It's not really ordered in any way, whereas a stack is usually one thing on top of the other, and it has structure to it. There's ways to do things. There's rules. So let's go a little bit into more detail about what a stack actually is. So, what is a stack? As you can see in the picture, it's a stack. It tends to be in high memory, and it is usually memory which is set aside as scratch space for a thread of execution, and it is managed automatically by the compiler. The heap, on the other hand, is typically lower in memory, and they grow towards each other. The stack is also used for function calls, such as like a new stack being created when a function call is created. Uh, Local variables, fixed length data, such as a list with a given size, return addresses, and parameters. Is there any questions about what the stack is? I think people should probably be a little bit familiar with the stack, but please ask any questions if you have any. Jeremy is scribbling furiously. Okay, if there's no questions, then I will move on. Okay, so now what is the heap? Now that we know what the stack is. The heap is memory that is also set aside, but it is used instead of for, I guess, automatic management by the compiler. It is used for dynamic allocation, and it's completely managed by the programmer for the most part. So unlike the stack, there's not really an enforced pattern to the allocation and deallocation of blocks in memory. You can allocate a block at any time and free it whenever you want. And this makes it a little bit more complex in the way it tracks which parts of the heaps are allocated and which are freed at any given time. So data on the heap is usually used for things like being assigned a pointer when you create upon manual creation with the use of malloc, which allocates memory, and it's manually freed and deleted using free. It's global, and it is prone to memory leaks by careless programming, as we will see in some examples. So over here in this picture, you can see sort of kind of like what allocating memory on the heap looks like. Essentially, just this is in C#, I believe, but in C you would just call malloc and assign space for something that you don't know the size of. For example, maybe you're taking, maybe you want to create a list, but the size of the list is totally dependent on the user. So you don't know what the size of the list is going to be. You're going to want to use malloc for that because you don't know the size of the list until runtime. Is there any questions about the heap? If not, I will continue. What is Cialloc? Okay, that's a good question. I think Cialloc does a similar thing. So I'm looking at the function manual page. So it allocates a block of memory for an array of num elements. Each of them size byte long and initializes all bits to 0. It looks like it's basically just initiating a list, or at least an array of things. Yes, and it does fill it with zeros from what I'm reading. There's more than one memory allocation function, but I think I'm just going to be focusing on malloc for today. But that's a good question. There are multiple memory allocation functions, and even mallocs differ across. They have different implementations across OSs or builds or things, as we will see in a bit. Okay, so if no more questions, I will move on. Okay, so we should probably know what the heap structure is. The heap structure is actually just a doubly linked list, and you can find this link here. I'm gonna post it in the Discord. I'm just posting it in the stream chat. So you guys can see that malloc, the struct malloc chunk is really just a doubly linked list where the size of the previous chunk is one integer, and then the size in bytes of the current chunk, and then a pointer to the block in front and the block in the back. The two bottom parts, actually, this is, whoops. I don't know why it's rendering them like that. That looks really bad, sorry guys. But yeah, the last two lines aren't too important. It's really just these 4 lines that are relevant for us. Is there any questions on the heap structure? And please let me know as well if I'm going too fast. Okay, I will move on then. Okay, so now we're going to do part 1 of this workshop. So that was just the quick review I wanted to get out of the way. So let's actually do a heap overflow now by reviewing what a stack overflow is. So if you recall a basic stack buffer overflow where we jump into a different function, it's very, very similar in that in both cases, we're trying to override things we're not supposed to. The only difference is that there's, I guess, less things. You could say there's less things to override in the heap for now, but you'll see it's fairly similar. So, like I said, a heap overflow is similar to a buffer overflow, where our goal is to write beyond the bounds of a single allocated chunk. So, a heap overflow can allow for adjacent allocated chunks of memory to be overridden or leaked instead of just overwriting. And this can lead to overwriting local variables or change addresses or chain pointers to things. So, for example, objects in the heap. That's probably going to be the most common thing because that's usually what most people put on the heap, just objects. But it's not the only thing. So, like I said, a heap overflow is trying to overwrite, I guess in this case, things that are allocated on the heap. Whereas a stack overflow is also overwriting things, but in that case, you're a little bit closer to things like the return pointer or other things that you can overwrite. Is there any questions? Okay. If there's no questions, I will continue. Oh, yes. So the heap is also space and memory and has a start and an end, but it's not, I guess you could say, as clear cut as the stack because there's multiple pointers in the heap that manage um, that basically manage what parts of the heap are free memory and what parts are being used. So it does have a start and an end, but it's not like the stack where like the stack pointer will point to the upmost thing on the stack, right? And it'll just go from there. And it's structured and it's ordered. Like I said, if we go back a bit, the heap is this, right? It's just kind of a mess. It's a heap. So that means that there's actually going to be multiple regions that are going to be free, and in between that, you could have regions of memory that are also being used. So even though there is a start and an end, the free, the free, the start of free memory doesn't necessarily have to be continuous all the way to the end. I hope that made sense. Okay. All right. If there's no more questions, you're welcome. Thank you for the question, by the way. Okay, if there's no other questions, I will head into the first exercise. Okay, so for exercise 1, if you got yes, this is live, Frisk. You can ask me questions right now, and I can answer them live. So if you have any questions, please ask them. Okay, so for exercise 1, uh, if you guys have already downloaded the files to download in the workshop material channel, we're going to be trying to exploit the first exercise. So it should be under EX1. And what I want you guys to do is I've actually provided you with a source code to make it easier for you. So you can read the source code and see what's happening there. And I want you to try to overflow the two adjacent allocated chunks of memory. I'm going to be hanging out in the in Discord as well if you guys want to ask me any questions. And we're going to do 10 minutes for this, so we'll probably come back at like 6:35 for this. I'm going to mute the stream and I'll be hanging out in Discord in the meantime. And also, don't forget, this is supposed to be a very simple buffer overflow, just to show you that it's not super different from what a stack overflow is. Oh, hey, sorry, Frisk. I just saw your question. So the exercises we're doing are in our Discord server. Uh, I'm not sure if you're in our Discord, but I can post an invite, I think. And you can agree to our rules, and our material should be in the channel called Workshop Material. How is everyone doing, by the way? If I do have some hints, but I'm not sure if you guys want more time or if you guys would like me to give out some of the hints I have prepared. Please let me know in the chat. I'm glad you liked it, Ethan. Okay, if there's no objections, I'm going to reveal some hints at least for the last 2 minutes. Okay, so uh, some of the hints I have here are the program is clearly printing the pointers of buffer1 and buffer2. And we know that these pointers are in the heap. So if you're having trouble getting started, try first calculating the distance between buffer1 and buffer2. Okay, so I can see that it's not a lot of people have solved the challenge. So if you're having trouble with it, please ask me questions or ask Alex as well. She has her DMs open. I'm going to let the challenge run for like 3 more minutes, and then I'm going to cover the solution. Okay, if there's no objections, I'm going to be covering the solution now. Okay, so let's actually go over the code. So this is what the code looks like. I hope it's not too small. Almost. You kind of have to scream at it in a bit of a specific way, not just straight up scream at it. But yes, it's very close, and I made it this way specifically because I wanted to show you that there's not a lot of difference between a buffer overflow and, or sorry, a stack overflow and a heap overflow. Okay, so in the code, we can see, like I said, buffer one and buffer two being allocated memory with malloc. And we know malloc returns a pointer, which gives us the start of where that allocated memory region is going to begin. Then we print the pointer of both of these buffers. And so now we know exactly where they are in memory. Then the next thing I do is I'm basically just writing, I think it's 10 A's into buffer 2. And then I print buffer 2 to show you that there's 10 A's. And then I print the size, printing, or sorry, then I print the number of bytes you're writing into a buffer, into buffer 1 specifically. And I'm also printing out the character you're writing into buffer 1. Then the program memsets into buffer 1 the amount of bytes that we decided to write. And then if you went high enough for your amount of bytes, then we will have overflown buffer 2. And then that's when I print buffer 2 to try to show you what your overflow has produced. However, if you want to get the flag, then you have to oops, this is not supposed to say that. Whoops, okay. Then if you want to get the flag, then you need to be able to overflow up until I think the 7th character, and then you want it to make it a U, I think. It's looking for the character U at the 7th or 8th character. I don't remember exactly. So let's actually go through the solution on the terminal. So I'm going to share my screen now. Okay. So all right. Let's go into exercise 1. Okay, so if we just run heap overflow, we can see it asks for an integer and a character. So we give it, let's say, the number 3, and let's give it the letter B. So we've written 3 bytes of the character B to buffer 1. Buffer 2 has remained unchanged. Let's write 5. Okay, so we see we're not affecting anything. Okay, so instead of trying to brute force this, we were given here these 2 addresses. So let's actually calculate the distance between these 2 buffers, because we know they're on the heap. So if we know they're on the heap, we should be able to calculate the distance between them and get the exact number of bytes we need to actually impact buffer 1. Give me a second. Minus. There we go, 32. I don't know what happened here. Okay, so we have 32 bytes in between those 2 buffers. So let's do 32 Bs. Okay, oh, now we're getting something interesting. So we have an invalid pointer, and then we core dump. So let's see what happens if we increase this by 1. Well, look at that. We've got our first B into buffer 2. So let's increase this to 35. And we keep increasing. And from the source code, we know that the buffer2 is actually looking for, it's looking for the letter, or sorry, not buffer2, the if condition at the end of the program is looking for the letter U. So we're going to change this to U now. And let's go all the way to 37, 38, 39, and there's our flag. Okay. So let's actually look at what's happening in memory. So let's GDB heap overflow 0. Let's break main. And let's run it. Now let's disassemble it. So, okay. Let's break to this printf here, right after this printf. Okay, sorry, no. Let's break. Let's break right here. And let's run this program with just a letter, or just 8 characters of the letter B. Yes. And then let's break at pointer. Then we're breaking at this memory address. So let's continue. Okay, so now let's examine these memory regions. So let's examine 30 hex at this memory region. Oh, I think I've enabled ASLR on this one. Just a second. All right, let's try that again. Okay, let's see. Okay, there. That's a little bit easier to see. We're gonna break here again. And let's run with 8 characters of the letter B. Continue. Okay, let's examine these memory regions. Oh, I can't examine the memory there. That's odd. Is it because... could be because of that. Okay. Disassemble main. Let's break here. Continue. Sorry, run it with 8 characters of the letter B. Yes. Continue. Examine 60 bytes from... why is it not letting me examine memory there? Sorry guys, it's a little odd. I'm not sure why it's not letting me examine memory there. It should allow me. That is odd. Maybe this one? Maybe if I try to break earlier. Let's run it again. Let's just step through the program. Okay, so I just have buffer 1. Okay, now it's letting us. Okay, there we go. I think I was breaking a little bit too late into the program. Okay. So let's try to break a little bit earlier, but after our memset. Our memset call is when we write our characters from the command line arguments into buffer 1. So let's break at memset. Let's just quit the program and rerun it again. Break main, run. Let's break. Sorry, let's disassemble main first. There's memset. Let's break at memset. Continue. Sorry, run in with 8 characters of B. Continue. Okay, let's do examine 60 bytes at. Okay, there we go. Okay, now we can see the heap finally. So here we can see the start of buffer 1 is at A0 right here. And we can see we've written some A's. I think, I can't remember anymore, sorry. I think ASCII table 41 is A. Let me just confirm that. Yeah, 41 is capital A. 42 should be capital B. So we haven't written our B's yet at A0. So as you can see here, at this memory address where our buffer 1 heap memory chunk begins is all just blank. It's all clear because we haven't written our B's yet. We're about to write them because we broke at memset here at this address in memset. But our buffer 2 has already been written, their A's, so 10 A's to be exact. And we'll talk a little bit about what this space here is, this region here. We're going to talk about what that is later, but for now, let's just go into the next instruction and let's write our B's. Okay, not written yet. Still mem setting them. Okay, now it's it just set them. So here we can see our B's being written. So we wrote 8 B's to be exact. And if we calculate the space in between these two between these two memory chunks, we can see it's 8, 16, and then 24, 32. And if you remember, 33 is when we finally reach our buffer 2. And we start overwriting our buffer 2. So what's happening is, let's try to run it again. This time we'll break at this memory address, just to make it a little bit faster. Okay, so let's run it again. But this time let's do 33, and we'll do 33 Bs. Continue. Let's continue, and let's examine 60 bytes at this memory address again. And as you can see, we've overwritten inside the heap. We've overwritten into buffer 2. Here's the buffer 2. Here's the first B of buffer 2. This is where the overwrite starts. And that's how that works. Is there any questions on that? I wish it was as simple as just sudo on GDB. And thank you for the compliment, Cosmicos. Very nice of you. If there's no other questions, I am going to move on now because I think I took a little bit too long trying to figure that out. Okay, I'm going to move on. So we looked at the heap overflow. Oops. That was exercise 1. So we've gone through the solution. And okay, so does anyone know why this program segfaults after you've overridden the buffers, or just buffer 2, I guess? And that's like a question I'm posing to everyone in the chat. So please make any guesses. There's no, well, I mean, there are wrong answers, but like, don't feel shy. I want to know what you guys think. Any ideas as to why the program segfaults? I'll give you guys a hint. It's actually because of the second free. Oh, so Cosmicos, I'm asking, why does the program segfault after you overflow it? So I'm going to share my screen again for a second. Okay, so I'm going to run this program again. Okay. That gets me the flag. So over here, why does it segfault here? Because Manzara saw my code. That's a good one. Cosmicos' guess is because the program tried to access memory, which is not allowed. Kind of in a way, but not exactly. Okay, Petiol is saying the program is trying to deallocate memory that has already been deallocated. Not exactly. It's not really a use after free bug. That's not why. But it is related to the second call to free in the program. Instant privacy because of the overflow. Don't know how. Yes, it is because of the overflow. If it wasn't because of the overflow, the program would exit normally. It overwrites some address. Not exactly. It's kind of like, it's very close to this, but it's not an address that it's overwriting. Yes, this is, I think, the best answer for now. Essentially, it frees memory, the memory address, but it is corrupted. No, the return address wasn't overflowed. That wasn't the issue. But I'm going to go into the solution now. Thank you guys for participating. Okay. All right, I'm going to go over the solution now. So the issue with the second call of free is that we're actually overwriting the malloc metadata. The Malloc metadata is this little bit of, I think it's literally just 1 byte that tells the program or the function free how to free the memory. It tells it the size of the memory, or the size of the allocated chunk, as well as how to do the call to free. So if we look here, data 1 is going to be the metadata for the first buffer. And we then put data into buffer 1, and then we overflow it. And after overflowing it enough, we start to overwrite the metadata from buffer 2. And if we override the metadata from buffer 2, free will have no idea how to free this memory because it has no idea what the size of buffer 2 is or what it's like, what the memory is there. It just doesn't know what to do. So I'll actually show you guys here really quickly where this metadata is. Okay, so let's go into GDB again. Break main, run. Let's break at, oops, not there. Disassemble main. Okay, let's do memset again. Break at memset. Oh, whoops, no. Break star memset. Okay, then we do run with 10 Bs. Yes, okay, continue. Okay, let's examine memory there. Okay. So over here, we can see buffer 2 starts at this address, and this address is right here. Before the buffer actually starts, though, like before this memory here, we can see this byte 21 right here in memory. This is what's being overwritten. If you remember, like up here, this is what we overwrote. This byte of 21 was right here, and we overwrote that. So when we overwrote that, we basically just destroyed any possible way for free to figure out what to do with this memory chunk. It just doesn't know what to do, and that's why the program segfaults. And I think this is important to know because if we're trying to fully understand how this exploit works and how it works, then these are things we should know because it can help us as both the programmer and the exploiter. Okay, so I'm going to stop sharing my screen now. Okay, let's keep going. Thank you, Cosmicos. All right, so now I'm going to explain really quickly how this metadata is actually calculated by Malloc. This is, oh yeah, quick disclaimer going into this explanation, by the way. There are actually different Malloc algorithms that allocate memory very differently. And even this is a very simplified version of what Malloc is doing. I'm actually giving a very simple explanation of what we call DL Malloc, which I think is, it was named by whoever wrote that Malloc implementation. And data 1 and data 2 are just bytes that are allocated when Malloc is called, like I previously said. So, okay. Also, oh yeah, and sorry, one more thing. The implementation is also dependent on the compiler, and that's also very important. So let's go through the simplified example. I'm just assigning letters here just to so that I was able to save myself some writing. But A would be free implementation, the way that the program is supposed to implement the call to free. So that's going to be 8 bytes. Okay, this memory chunk is going to be 8 bytes, and that's going to be part of the entire chunk. That's going to be the metadata of Malloc2, or sorry, the metadata 2 for Malloc from Malloc. Then B is going to be the actual buffer that where we're going to be able to write data in. This is the memory that's going to be given to the programmer, and this is going to be 16 bytes. Then there's also one marker, which indicates that this memory is being used, and that's going to be 1 byte. And so the final computation is going to be just 25 bytes when you add up everything together. And that's a very, very rough and simplified way of how Malloc calculates memory and computes this metadata for when memory needs to be freed. Okay, so now for part 2. We're going to be diving into what is called the global offset table and the procedure linkage table. So, okay, can anyone actually tell me how this code runs? And there's nothing else to this code. It's literally just these 3 lines. It's only these 3 lines. If you try to compile this code and you try to run it, how does it run? Why does it run? Sorry. Yes, it runs faster than Python. uh, yes, Cosmicos is pretty much right about with his 3 answers. It runs because of dynamic linking. And if you actually try to compile the program yourself and look at the compiler output, you'll notice that the compiler is going to start screaming at you because you're not defining things. It's going to tell you like, where is this printf coming from? What is exit? Do you mean this? And since functions are not defined, then they have to come from somewhere, and they come from libc being dynamically linked. I'm going to cover what dynamic linking is in just a second, but I just wanted to make you guys think about where these functions actually come from. So I'm going to share my screen for a second. Okay. So let's actually go. Okay. So let's do gcc externals.c. So if you look at the compiler's output, it yells at me for a bunch of different things. It tells me implicit declaration of function printf, which essentially just means that I haven't defined this function. And it tells me if I want to maybe include stdio.h, because that's where a declaration, or sorry, that's where a definition of printf exists. And similarly, the same thing for exit. It yells at me because I haven't defined it. And then it suggests that I should include stdlib.h. Okay, let me just unshare my screen. Okay. And actually, if you run the command ldd on the binary, you can actually see which libraries are being loaded dynamically into the binary. So let's actually go into a little bit more detail about what dynamic linking is. Dynamic linking is, it gives us a lot of flexibility to compile programs. It essentially, instead of having static libraries for each program that you have to compile to compile them all with, like just each of them having their own library just for that program. You can have these things called share libraries, so that you can always reuse your code amongst programs. This lets us have smaller programs, and it also allows binaries to receive updates without actually being recompiled. And it should also technically make programs portable, but it's not that portability isn't that simple. But dynamic linking also requires a program to know the exact addresses of functions to be able to create call instructions. So we kind of run into an issue of how the program is going to know where things are in different versions of libc, or if libc is protected by ASLR, for example. It's not going to know where things are unless we introduce the global offset table. So what the global offset table then does is a little bit more of a redirection, I guess you could call it. First, we have, for example, here the call to printf, which is put on the procedure linkage table, which is just the shared library where these shared library calls are made. Then from the procedure linkage table, we are going to map this call jump to global offset table at address n. We're going to map this call, and we're going to have this entry in this table called the global offset table. And this PLT entry address is going to redirect back to the procedure linkage table entry, and the code finishes executing this function call. This is what it looks like before lazy binding. And then after lazy binding, what will happen is the program will dynamically add the address of printf, for example, here. This is quite a bit to take in, so please ask questions if it's not very clear. Okay, if there's no questions, I'm going to share my screen now and actually show you a little bit more detail how this works. And feel free to follow along as well. Okay. Okay, so I'm actually going to call Ghidra. Okay. Okay, so this is the same program we had earlier before with just a call to printf and the call to exit. So as you can see here, this might be very small to see, but right here we have this call to an external function. It says call external put s, and there's no function here. If we try to follow it, we just get what is called the thunk function, which is just a stub function. And this function exists on the procedure linkage table. And what it does is it's going to eventually call the program at the global offset table, procedure linkage table entry here for puts. So this is where the program is going to link the real address of puts, which comes from libc. So let's actually look at it another way. Oh, whoops, that's not what I wanted to close. Exercise 2. Okay. Let's do, okay, GDB a.out. Oh yeah, and if we do LDD on a.out, we can see the libraries that are dynamically linked on this program. libc.so.6 is one of them. And I believe this is the dynamic linker. Okay, so let's do PID of, process ID of a.out. Oh, right, I have to run it first. Okay, there we go. Now we have a process ID. So let's cat proc res maps and then shift insert. Whoops. Maps. Doesn't want to. Okay. Honestly, that's probably not that useful anyway. But anyway, yeah, this is, I guess, what I wanted to mainly show. A band called them. But yeah, this is what I really wanted to show you guys, though. The different how the different external functions are being linked. The global offset table will have an entry here, which is going to be the real address of this function, which is going to come from libc. And in the PLT section, we're just going to have a thunk function to puts. We're just going to have this thunk function to puts. Okay, so this is something you can do in Ghidra or most D compilers, I believe. Okay, so now let's actually do something. Again, let's actually do an exercise now. So in the no includes program, I want you to find the global offset table address used for the call printf from the source code and give the address in decimal to ORCID for points. So I will start you off with a little bit of a hint. You want to use disassembly. So because let's actually go back to this this slide here. If you remember, the code here, this is the source code. It's going to call printf, which is going to jump to the procedure linkage table, and then the procedure linkage table is going to jump to the global offset table, and then this is going to jump. This is going to have the real address of printf eventually. So this means you need to run the program in GDB and find this address here. And you can do it by disassembling each call. and following along. I'm going to give about 10 minutes for this as well. And I actually, yeah, just a flat 10 minutes. I'm going to give some hints at around the 5-minute mark because I think I'm running a little bit short on time. And if you have any questions, feel free to ask. So just to make sure you guys are on the same page, this flag doesn't have the UC-sec curly brackets format. And also another thing I wanted to mention. Oh yeah, to convert the hex address into decimal, just run it through Python and give it the hex number. So you can just call Python, and then you'll be in the interactive Python, and then just copy and paste the hex number, press enter, and you will have the decimal number. Okay, we're also at the 5 minutes mark, so I think I am going to be showing some hints because, like I said, I'm running a little bit short on time. Okay, so some hints for this. Don't forget to break main and run the program. I know I did this myself by accident. Uh, disassemble GDB command is your friend. So for each call that is made, remember to disassemble it. And now I did use a little bit of tricky words, I guess, because printf is not actually going to be called in the program. It's going to be putS. And this is because GCC optimizes printf to puts when there's no formatting. When there's no other arguments provided to printf. Yes, exactly, when there are no arguments. Hi, Pickle. There's still quite a bit left if you want to join us. You can find the workshop material in our workshop material channel in our Discord. Okay, I'm gonna give 1 more minute and then I'm gonna go over the solution. I think object dump might be enough, but I honestly can't remember. Okay, I'm going to cover my solution now. It might have been possible to do it through object dump. I am honestly not sure. I think it, it would be interesting to see, but I'm just going to cover my solution for now. Okay. So let's go through the solution. Okay. So first, we want to run no includes through GDB. Then we want to break main. We want to run it. Then we want to disassemble main. And then here we can see the call being made to puts at the PLT, just like what we saw in one of the diagrams. So we're going to disassemble this call at this address. And here's where we're going to get our flag. So the address of puts at the global offset table is going to be this. So this is going to be the real address of this of the call to puts. This is the address of puts in libc. And if we run this through Python, we're going to get our flag. Okay, so let's continue if there's no other questions. Okay, I'm going to move on if there's no questions. Okay, so why would we want to overwrite the global offset table in this case in a heap overflow? So the answer is one, sometimes it's not really feasible to overwrite a stack pointer due to shifting addresses, such as ASLR. Two, there's a lot of memory that would need to be overwritten to get all the way out, to the stack pointer. So if you see where the stack is and where the heap is, there's a lot of memory in between that would need to be overwritten, and that comes with its own issues. Or finally, a call to the exit function is made, and the program can no longer return, which means it's not going to be able to jump. It's not going to be able to return and jump to where you want it to go. So those are some of the reasons why you might want to override the global offset table, and we're actually going to be doing it in a bit. So for now, let's actually start overwriting, or let's actually try to take control of program control flow. I'm sure you guys know string copy is not safe, and we should have now enough knowledge to be able to exploit a heap overflow with this. As you guys should know, string copy is pretty much free real estate. So for exercise 3, I want you guys to analyze heap overflow 1 binary and jump into the function containing a flag. So I've also provided you with a source code for this challenge, and the previous challenge should have helped you sort of figure out how to get addresses. And yeah. So if we can do this one, and we'll say like another 10 minutes, maybe 10, 15 minutes, and then I'm going to, I think I'm going to do hints at the, at 7:40, and I'll let you guys work in silence. One thing I would also note though is that I think I also did give you guys um, a template inside exercise 3 called exploit.py, which should make it a little bit easier to complete your exploit. No worries, Cosmicos. Thanks for participating anyway. How are people doing? Let me know if you have any questions. I'm going to be providing some hints now. Um, you want to, one, calculate the distance between the two different structs and the program, similar to the first challenge we did today. And I also posed the question, how is the FP variable, how's the FP variable being used? And if you're also having trouble finding the address of the win function, uh, you can get it by typing info functions in GDB. I'm going to leave this for 5 more minutes and then I'm going to cover the solution. Okay, I think I'm going to be covering the solution now unless there's any objections. going once, going twice, giving it a 2 seconds for the stream delay, going thrice. Okay, I'm going to go over the solution now. Okay. Let's quit out of this program. Okay. Okay, so we have Heap Overflow 1. So we have data is at this, and then function pointer is at this address. So if we're just trying to follow this this program or this template right here, all we need is to figure out the padding that we need, and we need the address of the win function. So let's just try to do that first. The address of the win function is the easiest, so let's go for that. Info functions, and we have the address of win right here. And then we want to type this out in Little Endian. So I think it should be 56, 11, and 40. So that's the same address, but in Little Endian. And then now we need to figure out the padding. So if we run it, if you run the program again, we know both of these structures are on the heap, right? If we look at the source code, both of these are being allocated and they're being placed on the heap because they're being called with malloc. So let's calculate the distance between these two. And the distance is going to be 80 bytes. So if we plug in 80 bytes at the padding, and then we write this, we run the exploit, and you see we get our flag. Okay, but let's actually try to understand what's happening here. So let's break main, run it. Okay, let's disassemble main first. Let's look at the program. Oops. So I hope you guys know what function pointers are, but all they are is pointers which to which you can assign the address of a function, and then you can just call that function pointer as we do here instead of calling the function itself. So what this program is doing is it's allocating data, or sorry, it's allocating memory for this structure right here, function pointer. And then after allocating memory for it, we are assigning the f attribute. We are assigning f here, which is the pointer which points to that structure. And then we assign fp, the address of no winner. And so when we assign it the address of no winner, we can just call no winner like this. So what we're doing, the goal here is to use the string copy that's happening here at name. We're going to use that to get to this struct right here and overflow and overwrite this function pointer and take control of it and redirect it to a function we want to jump to. And this doesn't even necessarily have to be this function, this win function. That's the cool part. It could actually be like a gadget, or we can create a return to libc exploit or something else. But for now, we just redirect it to this win function. So that's what we're trying to achieve here. And that's why we need to first calculate the distance between these two structures in memory and the heap. So let's actually look at what's happening in memory. Okay, so we've disassembled main. Let's break the string copy. Okay, so let's run this program with, let's say, 60 bytes and I think just 60 bytes. Yeah, just 60 bytes. So here the program is telling us that data is at this address. So let's examine some memory there. Examine 60 bytes at this memory address. And we can see that it's all just zeros because we haven't actually we haven't executed the string copy call here yet. But we can see that this other structure, the FP struct, is right here. And we can see the address of no winner. So let's actually check the address of no winner. What is it? The address of no winner is 40.11.6c. And as we can see, that's the same address that's being assigned to that FP structure. So let's actually go through our string copy. Okay, we're back in main. Let's examine that memory region again. 45A0. Okay. Looks like there's nothing yet. Okay, let's run it again. Let's disassemble it. Let's just break right before the leave. Okay. Run with 64. Oh, right. That's because we're supposed to give it a really long string like that. Continue. Continue. There we go. Now you can see all these A's. These are all lowercase a's. And if we can go far enough, we're going to be able to overwrite this function pointer and redirect it to somewhere we want it to go. And if we, for example, redirect it to the win function, this call at the end of the program, is going to call that function pointer, and it's going to execute whatever is at this address. It's going to call whatever function is at this address. So let's actually see what happens if we go far enough. We get a seg fault. And why is that? because we've overwritten the address here. And the program doesn't really know where to go anymore. And that's how this exploit works. That's how we can take control of the program using a buffer overflow and a function pointer. Is there any questions for this one? We're almost done. The last one is the final challenge, and it's kind of cool. If there are no questions, I will move on. Okay, so that's the Heap Overflow 1 code. Okay, now, and that's the Heap Overflow 1 solution, which we just covered. And that's my solution. Okay, so what we know so far. We know how to do a basic heap overflow. We know how to use string copy to overwrite memory. And we know how to obtain global offset table addresses. So can we use all of this to redirect a function in the global offset table? Well, the answer is yes, and we're going to put it all together. So instead of overwriting a function pointer, for example, with instead of overwriting a function pointer, we're actually going to overwrite the entry of a function in the global offset table. So I want you guys to use everything you've learned from the previous exercises and analyze the heap overflow 2 binary and redirect the program to obtain a flag. So some useful tools are going to be GDB and pwn tools. And I've also provided a template exploit that you can use to make it easier for you to get the flag. And I've also provided you with a source code. Make sure you read what the source code is doing so that you can understand what you're trying to do in memory. Because if you understand what you're doing in memory, then this becomes a lot easier, I guess. In this program, it also might not be super obvious how you're going to achieve a redirection, but it is possible. And make sure you look at the second string copy in the program. And please ask questions if you have any. My nickname in Discord is Inga. You might have also seen Ingabot. That's not actually me. Listen, guys, Ingabot has taken my quotes out of context, so it's not accurate. Okay, I'm going to provide some hints now, and I hope if you're stuck, it'll help you move forward. So, one thing to note, and I kind of alluded to this previously, Malloc will do things differently depending on what you're doing and depending on which Malloc you're using. The Malloc we are using likes to align things by 8 bytes. This means that if you have, let's say, a piece of data that only requires like 4 bytes, Malloc will not really give it 8 bytes, but it's going to essentially allocate 8 bytes for that for data, or for byte data, because it likes to align things by 8 bytes, like I said. And if you remember how to obtain global offset table addresses, that's going to be very important, because there's one function at the very end of the program that's called, that you can use to redirect your the program to somewhere where you want to go. And finally, the second string copy is the key to this redirection. I think I'll give like 2 more minutes for this, and then I'll cover the solution. And I don't think we'll be too much over the time limit for today. Okay, I'm going to be going over the solution now if there's no objections. So this is the Heap Overflow 2 code, and I'm going to be going over my solution now. So let's take a look at the Heap Overflow 2 code. So we have just one structure this time. But the difference here is that we're going to be creating 3 structures and allocating memory for 2 of them. So even though there's only one structure, there's still technically going to be 2 different structures in memory, each with their own address of where they start. Now, if you look at the wording here of this printf carefully, it's very, it's a little bit, I guess you could say, misleading. Because let's say we're just trying to follow the template here, right? If we're just trying to follow the template, we just need a padding, the puts global offset table address, and the win function, and the win address. So let's run heap overflow through GDB. Let's get the address of the win function. Oops. So the address of the win function is going to be this. So 561140. 56, 11, 40 and little endian. And then the puts global offset table address. So let's run this, break main, and then run with just, let's say, whatever. Let's disassemble main. Here's a call to printf. Let's disassemble that call. And here's our address to, oh, sorry. We want to disassemble the call to puts, not printf, sorry. There it is, the call to puts. So it's going to be 20, 40, 40. 20, 40, 40. And then the padding, which is going to be the slightly misleading part. Oops. So if we calculate the different addresses, minus, oops, 0x, we're going to have 32 bytes. So if we do 32 bytes, we're going to see that we don't get anything. This is actually just going to make the program segfault. And the reason is because, like I previously mentioned earlier, the way the structure is being created here, it's not actually going to be just 4 bytes and then 8 bytes as we're allocating for the name here. Because normally an integer is just going to be 4 bytes of memory. And then char star name is just going to be whatever the length of the name is. In this case, I think it's just going to be 8 bytes because it's an address. Or it's going to be an address pointing to where the actual string is. So because this is 4 bytes and this is going to be 8 bytes, Malloc is going to want to pad this space in priority. It's going to want to pad it to 8 bytes so that it aligns to 8 bytes with name as well. And we'll take a look at this in memory right now. So let's break main, run it. Let me just see which arguments it needs. It needs 2 arguments. And it's going to be the names of each struct. Each internet structure. So let's run it with A and B. And let's disassemble. And let's break right here. Whoops, nope. Break star. Continue. Okay, so now let's examine memory here. Examine 60 bytes at. So we can see that I2 starts at 4052C0. So we can see the name is here. And then I think the priority should be right here. Sorry, just a second. So we have in priority. Okay, so we set the priority to 1 here and the priority to 2. I think we might have overwritten the priority. Let's run it again with 1, 2, 3, 5. Let's just run it with 4. Did we overrun it? Give me a second. Okay. Did we overrun it? I don't see where the 1 is. Why isn't it appearing? Okay. Sorry, for the sake of time, I'm just gonna quickly cut through this. But anyway, so the point is we're gonna be able to overwrite all the way to this this address right here, 4052E0, 4052E0. This is the priority 2 here that was set here. That's going to be that priority 2. And as you can see over here, it's going to actually be 8 bytes total because it's going to want to 8-byte align it. And this address right here is actually going to lead us to our BBBBs. As you can see, 405-300, 405-300 takes us to this set of strings, which is just our Bs that we set earlier. So what's going to happen is with this overflow, we want to overwrite all the way to this address because the second call to string copy is going to go to this address, whatever this address is, and it's going to write whatever we want it to. So for example, in this case, we're not doing anything crazy. So we're actually just telling string copy to go to this address right here, 405-300, and write a bunch of Bs. But what if we change this address to, I don't know, say the global offset table entry for puts? Then we're going to be able to overwrite the entry for puts and redirect code wherever we want, pretty much. So let's actually do that. And the first step is to figure out how many bytes we're actually going to need. So let's run this with, let's give the first name, let's give the first internet struct a bunch of bytes. Continue. So we finally got a seg fault. Do we have enough to overwrite this? 405-300 at 405-52E0. So we're going to overwrite up to here, which means we need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're going to need 10 times 8, which is going to be 80 bytes again. So I think if we do 80 bytes, that should be right? 4, 8. Oh, sorry, no, not 80 bytes divided by 2, 40 bytes. That should be 40 bytes. And if you remember the previous number we got from calculating the distance between those two addresses that I printed out, we got 32. But again, because Malloc likes to 8-byte align things, we're going to add 8 bytes to account for the int here. We're going to add 8 bytes to account for this int priority. So we're going to do 40. And then we already got the addresses set. So let's do Python exploit.py. And we can see our flag is right here because we've successfully overwritten this address right here. Let's do U. Let's examine that memory region again. And we can see we can successfully overwrite this memory. And the second string copy is going to go to this memory address and overwrite whatever we want. And that's going to be the end of that solution. And if you want to continue heap exploitation, then you can also do these challenges in this thing called exploit education. There's this path called Phoenix, which takes you into more detail and does some harder challenges. I hope you learned from this workshop, though. And credits to Live Overflow, because a lot of this was from his videos. Anyway, that's it for this workshop, and thank you for attending. Don't forget to fill out the attendance sheet, please. And have a good night, guys.